would like to thank all you guys to come here, and then I think that we have to learn really much from you, because we have some ambitious project, but then, I mean, we come from different fields, as you can see. Different fields. This is the work in collaboration with people. It's from dynamical system, quantum transport, disorder system, so nothing to do with biology, with chemistry. But, okay, so from this point of view, we have to learn a lot, and this is the story. Today, I would like to tell you a story. The story of this, our first paper on this subject, okay? And, okay, I can skip, because Mohan made a beautiful introduction on how light harvesting complex works. So let's say the fundamental question, then he already did, but, you know, just also for students, then in the FMO, which I would like to concentrate today, which is the transport of excitons. There are very high transport efficiency, and many questions can be posed and many answers can be done on how coherence is maintained in this FMO system. And okay, now I'm very glad that the experimentalist people says, what about quantum coherence? I would say from a theoretician point of view, there is no matter of choice, because if you simulate Schrödinger equation, this is quantum effect. If you simulate classical, then this is classical effect. But of course, experimentalist is very difficult. I agree that. But in any case, I would like, okay, this is also can skip. So we are concentrating on this FMO, which is 7 sites. And just to remind you what are the relevant time scale, and just to have in mind, there are many time scales in this problem, which is the exciton recombination time, which is roughly 1 nanosecond. By the way, it's not that easy to find a relevant number for this, because in each paper you can find 2 orders of magnitude difference between one number and the other, but nevertheless, exciton recombination times, it means that exciton can disappear as a photon again, and this is the time, 1 nanosecond. But this time is, you know, 1 nanosecond is 3 orders of magnitude different from energy relaxation of this exciton at room temperature, which is, okay, let's say order of 1 picosecond. Also, there are 2 other relevant time scales, which is the exciton dephasing time scale, which is order, I would say. Please correct me if I'm wrong, because of course, just taking some data, but maybe. Exciton dephasing time scale, I would say that is order 100 femtosecond, and also phonon correlation time, which is order 50 femtosecond. Okay, the tight binding Hamiltonian for exciton is very simple. Just the tight binding Hamiltonian, because when you put bath, as Mohan showed, there are 100 billion possible bath and approximation, and a lot of difficulty, a lot of different approach, and okay. But at least the tight binding Hamiltonian is very easy. You have, in this complex, you have 7 sites. These are energy, and this is coupling. And typically, coupling and energy difference, energy distance between levels are the same order of magnitude. Energy here is measured as a frequency in centimeters minus 1. So it's very useful scale. Sorry. If you look like just this, say, closed system, this is a closed system. If you look at how this coupling and energy looks like, it looks like a disordered system. Of course, it's 7 by 7 matrix. One could say this is really disordered, but there are no, let's say, no idea how Y should be ordered. So you can speak about a disordered system. Okay. Of course, the interesting in just open this system, and so that's why we switch to the very much more complicated problem of open quantum system. Okay, so I would like to divide the problem in 2 different let's say, subject. One is how we take into account dissipation. When we talk about dissipation, we have in mind two kinds of dissipation, which is the dissipation due to the exciton recombination, in the sense that the exciton can disappear and create a photon again. And also we have dissipation with the reaction center, in the sense that we are just looking on the reaction center as a sink. Okay? Your excitation can disappear in a sink. In this sense, these two kinds of dissipation can be modeled using an approach which is well known from our group, which is the effective Hamiltonian, which Valentin was talking about just before. And just reserve our consideration about the other very delicate problem of phonon environment and phonon thermal bath just at the end, okay? So let's talk about our closed system and with dissipation, okay? Dissipation due to exciton, recombinant, and to the sink, to the flow to the sink, which is the reaction center. Okay, so let's concentrate about the effective non-Hermitian Hamiltonian to model the first one. Just to, let's say, our idea was just to meet different communities which are talking about this non-Hermitian Hamiltonian. They come typically from nuclear physics, okay? So you have some intrinsic states which are coupled to some open channels. And then you consider this amplitude, or this transition amplitude between this intrinsic state and these channels, these open channels. This problem, this approach is not perturbative, and it has been applied in many different situations: quantum transport, mesoscopic electron system, nuclear physics, and so on. This is just to give you some idea. And the model that you have to consider is just to take into account an effective Hamiltonian. An effective Hamiltonian means that you have the Hamiltonian of the closed system, and then your W, which is a Hermitian Hamiltonian, which so this is not Hermitian, so this is a not unitary evolution. And this has a well-defined form, which is given by this transition amplitude. Of course, if you diagonalize this kind of Hamiltonian, you have some complex energies. And the complex energies are some real and imaginary parts. And the imaginary parts represent the amplitude, the decay, to this channel. Okay? And inside this kind of problem of this open quantum system, of course, we are talking about superradiance. Superradiance is also in my title, but now I would like to explain what we mean in this context to superradiance. Okay, the effect of opening can be summarized very briefly in some energy shift of the levels and some finite lifetimes of the levels. Okay, so you have a width, so you have some probability to decay. And what happened typically then when the coupling to the open to the sink is small, all these internal states are affected quite similarly by this opening. It means that the lifetime decrease as the coupling increase. Okay? But what you are beyond some critical value, some states become short-lived. They quickly radiate, and all the other states are effectively decoupled from the environment. One rough estimate of, and this we call superradiance, okay? So one rough estimate is when the width, the gamma is the average width, become of the order of the distance between levels. And this is the criterion for superradiance. Okay, this is superradiance has been used using random metric theory since long, and also in quantum transport in many different papers and people in the world. Okay, how we would like to apply this approach to this problem, which I would like to remind you that this is just a closed system with sinks. Okay, in our approach, sinks are channels in nuclear physics language. We have one channel for each site, which represent the possibility of the exciton to recombine in one photon. And moreover, we have one more channel, which is the reaction center. So we have 7 + 1 channels. Okay? This is the possibility to decay. Of course, we can calculate easily the amplitude. As you can see, T1 is the recombination time, which is 1 nanosecond. And T1R is our coupling parameter, which is described the coupling time with the sink. Okay? So we can study just this problem, as you can see, without any heat bath, and just study what is the superradiance transition. When superradiance transition occurs for this system, okay? This is just, let me remind again, this is a closed system with dissipation, no bath at all up to now. Okay, this I will skip, okay? Okay, this is, for instance, how the K-width looks like when a superradiant transition occurs. Okay, the red curve is the, let's say, is the state with the largest width. And all the black curve is the average over all the other. As you can see, at the superradiant transition, one states take all the width, almost all the width, and became superradiant. Okay? Of course, we couldn't speak with the community, chemistry and biologists, without taking into account some bath. But since we are not expert in this kind of stuff, we just take the simplest bath as possible. We take into account two kinds of bath, just taken from literature. One is just called dephasing. And this is a bath which has been considered by many, and is just taking, one should take into account some Hamiltonian, which is diagonal in the side. Qi are bath operators, and they satisfy, they are time dependent, so this is why I call classical noise. And this defines some dephasing time and the dephasing rate, which has been measured experimentally as a function of temperature. In some range is almost linearly dependent from temperature. This gives rise to Haken-Strobel master equation, which has, as you remind, many limitations, but nevertheless, you can have some kind of, okay, this is your coherent evolution, this is dissipation to the sink and to the channel in each sides, and this is the terms given by this dephasing interaction with the phonon bath. This is the first kind. As you can see, what is affected is just the diagonal relaxation, okay, in the matrix element. Okay?
You should have probably term of gain term. You have.
Yeah, of course. But this is.
Gain term.
Okay, this is.
What's term? Something.
Okay, this is the dephasing. Okay, the dephasing, you see, this is just off diagonal. Yeah. It couple off diagonal.
Second term, dissipation.
The second term is the dissipation, just due to the sink.
And lost, reaction center.
Reaction center, exactly.
I think it's just gain term. Reaction center produce you.
No, it's sink. It's a sink. It's just a sink.
Photons.
No. Okay. When exciton go to the sink, it disappears. Sure. Okay. Okay, let me just show you what happened. For instance, just look at this small. This is obtained with very small temperature. So it means that even if you neglect the coherence, the influence of the bath, you have some curve like this one, the black one. So this this is the efficiency, and this is the superradiant transition. How the efficiency is defined is just written here. This is just the integrate probability to arrive at the site number 3, which is connected directly with the sink. When you arrive at site number 3, you just flow in the sink, okay? And this is the rate, okay, the rate at which this occurs. Okay, what we can observe then, the efficiency has a maximum very close, okay, not exactly the same, but also this criterion is not exact, very close to the superradiant transition. And this is without bath, any bath, no bath, no, just sink. And this is a function of the coupling, okay, this is a time, so in this direction the coupling with the sink becomes smaller, and in this direction becomes bigger. So as one can see, at the superradiant transition, efficiency of the transport is maximal, very close at least. Also, you can observe that this value of the coupling is considered to be not much realistic, because it's order of 30 femtoseconds. Nevertheless, the average transport times at the superradiant transition is order of few picoseconds. Okay, but you know, this is, as I told you before, this is also a story with a long battle with the referee. So they were not so quite satisfied with this, our approach of this bath. So they asked to introduce real Gibbs bath. And we did in the simplest way possible, not using this very complicated stuff as Mohan showed, not a hierarchic equation, just the easy way to do, which is by adding some Lindblad terms, using the whole approximation, weak coupling, secular, Born-Markov. This is really a lot of approximation. So, but nevertheless, people also are doing such kinds of stuff. So this machinery, we took this machinery from this paper, but it's well, I mean, many people are using this. And okay, of course, when you introduce this kind of bath, there are two more parameters, which is the reorganization energy here, which represents some kind of decoupling with the bath. And also there is some cutoff frequency, which they measure, it seems to me, experimentally, just fitting with the phonon spectral density. And this cutoff frequency indicates somehow the degree of Markovianity of our bath. As you can see, this changed a little bit, because in presence of temperature, this is the red line. Okay, this is 300 Kelvin, this is the efficiency, and this is the average time. But you see, the maximum of efficiency stay close to the superradiant transition. So, in a sense, this mechanism, I mean, if we are looking for what happened at the efficiency in the open system, just close plus dissipation, I mean, this green line has been obtained just taking into account dissipation only, without any bath. We have some maximum, and we have the maximum of efficiency is very close to this value. Okay?
The initial state is still 160.
Yeah, it's the same. But it doesn't change. We also make different initial states. And we also make other different approaches. I mean, more or less the same. Also different coupling with the reaction center. For instance, we can connect two chromophore to one sink. So more or less is the same. Okay, this is dependence on bath frequency. Of course, if we change cutoff frequency, efficiency change, but also as a function of, this is a cutoff frequency, this is a coupling with the bath, reorganization energy. But still, you know, the maximum is very close, so this is quite robust in a sense. One could wonder if this, since everybody says that this has nothing to do with classical, this is evidence of quantum transport and such kind of stuff, we would like to show that if one deals with a classical kind of master equation, a completely different picture happens. For instance, we can introduce some classical master equation. As I told you, for a theoretician, it's very easy to make classical. No? You take only population. This is population. There are no off-diagonal matrix elements, so this is classical. Okay, so this TIK are transition rate, and these are are given by some Foster theory. This was taken by this beautiful paper by Leakwater. Okay, what is these guys? This J, I, K are the electric dipole coupling between the I and K site. This gamma phi is the coherence rate. And this delta E naught is the difference between the unperturbed energy level spacing. As you can see, this TIK rate does not depend on temperature, they depend on temperature only through this factor, okay? And of course, this is the loss due to the exciton recombination, and this is the loss to reaction center, to the sink, okay? This is classical master equation, very simple. And this is the result of classical and quantum simulation at 300 Kelvin, okay? As you can see, for small coupling here, this is the region of small coupling to the reaction center, classical and quantum simulation are pretty much the same. But here, at some point, they deviate strongly. Not only they deviate, but the behavior of classical should be monotone from the formula above. While classical, we have a bump. I mean, here, efficiency decrease when the coupling becomes large, the coupling with the reaction center, sorry. So let me do some consideration, and okay, let us consider this regime. Okay. In this regime, when the coupling time is much bigger than the critical value, which is the superradian, so it means small coupling to the reaction center, the average time spent in the FMO is quite large, and the efficiency of energy transfer is pretty much the same as in the classical case. So this is the right side of the picture. This is our, let me say, rough interpretation. On the other hand, when you have large coupling time, this time becomes small, and in this case, quantum description becomes important. Okay, this is what I already told you. And okay, well, there is no time. I would like just to leave you some time.
There is 10 minutes.
Yeah, but I would like not to be. Okay, let me switch to physical interpretation. Why efficiency is maximal at the superradiant transition? Okay, we don't know, of course, but we can give some, let's say, some rough estimation, some rough argument of this phenomenon. And we may say that, okay, for small coupling time, which means when the system is strongly coupled to the reaction center, all states are strongly localized. We also measure participation ratio of the state. So we have strong localization in this case. So the only state which can decay fast, which is the superradiant state, is localized very far from the sites where the excitation starts, because excitation starts from one side, okay? And we are measuring the time to reach the sink, which is in the other side, opposite side. So it means that the efficiency cannot be optimal, because, you know, there are no overlapping. So we are in a strong localized regime. On the other side, when we have a small coupling to the reaction center, the states, all the states, have a very small decay width. We are thinking about this problem in terms of superradiance. So they can hardly decay, since the decay width is very small. And in any case, the exciton, we have already seen that it's performing some kind of, random walk, some classical walks among excitons. So no quantum coherence, because the motion is more or less classical. And so even in this case, there can be an optimal efficiency. Of course, we can expect that, so there should be some trade-off. And this at the superradiance transition, both effects can be mitigated, and since in some sense localization increase with respect to the first point, but decay increase also with respect to the second point, and the maximum can appear. Okay. This is conclusion and perspective, and of course the superradiant transition, we see that strongly affects the transport. We wouldn't say that bath has no influence. Of course, it has a lot of influence. It depends from the bath you take into account, from the temperature, from the characteristic of the bath, no Markovian. There are a lot of stuff to do again. But what we'd like to just point out that superradiant transition, I mean, is a robust phenomenon which occur even without any bath consideration. Any bath can be taken into account. Also, okay, this I didn't show, but with superradiant transition, we could find the optimal parameter from the distance to the reaction center. We found values from 1 nanometer to 3 nanometers, which is quite in agreement with experimental data. And of course, we believe that by playing with superradiance and disorder, we can give much more information on this kind of phenomena. Thank you for your attention. This is our paper, which will be appear on Journal of Physical Chemistry C, our first paper on. Thank you very much.